My talk is about hardness approximation of k-clique. Given a graph G and a positive integer k, the k-clique problem is to decide if G contains a complete subgraph of size k. It is well known that k-clique is NP-hard. Assuming P is not equal to NP, it has no polynomial time algorithm. In parameterized complexity theory, k-clique is W1 hard. The hypothesis W1 not equal to FPT is equivalent to stating that k-clique has no FPT algorithm. A relaxed version of this problem is gap k-clique. In the gap k-clique problem, we want to distinguish two cases. The yes case is G contains k-clique, and the no case is G contains no 1 minus epsilon k-clique. We already know that gap k-clique has no polynomial time algorithm, assuming P is not equal to NP. And the proof of this result requires the famous PCP theorem. A natural question is, does gap k-clique have an FPT algorithm? Previous work shows that the answer is no. These works are based on some strong assumptions. So an open problem in parameterized complexity is to prove gap k-clique has no FPT algorithm under W1 not equal to FPT. It is believed that we might need a parameterized PCP theorem to solve this question. The main result of this talk is to prove the W1 hardness of gap k-clique. Before moving to the detail of our proof, let's see how to prove hardness result of gap k-clique in the classical framework. The proof contains two steps. The first step uses PCP theorem to reduce k-clique to the CSP problem. Recall that an instance of CSP problem contains variable set X, constraint set C, and alphabet D. The goal is to find an assignment satisfying all the constraints. For every instance I of CSP problem, we use value of I to denote the maximum fraction of satisfiable constraints. An important feature of the PCP theorem is that it creates a constant gap. More precisely, if G contains a k-clique, then the value of I is equal to 1. And if G contains no k-clique, then the value of I is less or equal than 1 minus epsilon. Once we have a constant gap CSP problem, we can apply the FGLSS reduction to obtain an instant of gap k-clique. Thus prove the hardness of gap k-clique problem. Note that all these reductions are polynomial time reductions. In parameterized complexity, we have an additional requirement for the reduction. We cannot use a reduction that makes the parameter depends on the input side. Unfortunately, the PCP theorem does not satisfy this condition. So let's take a close look at the PCP theorem and see if we can fix the parameter problem. The proof of PCP theorem repeatedly apply the PCP main lemma to amplify the gap between the yes case and no case of the CSP problem. If we start from an NP-hard problem, then D is constant, X is N, so M is poly N. We might need to apply the PCP main lemma big O log N time. If we start from a W1 hard problem, we might need to repeat the PCP main lemma big O log K times. At first sight, it seems that the PCP main lemma works well in the parameterized setting. Unfortunately, the problem is this lemma requires the alphabet D to be constant. So again, let's take a closer look at the PHP main lemma and see if we can do some hack on it. The PHP main lemma contains two steps. The first step is gap amplification. It amplifies the gap, increase the alphabet size. So we need the alphabet reduction to bring the alphabet size to constant with a small loss of the gap, and also increase the number of variables. If we reduce from an NP-hard problem, D is constant. An exponential of a constant is still a constant, so everything is okay. However, if we reduce from a W1 hard problem, D is n, and exponential of n is not allowed. So the conclusion is we might need a parameterized version of alphabet reduction to prove the W1 hardness of gap k-click. In this talk, we saw how to apply the technique of alphabet reduction in an FPT reduction. So let's move on to the technique of alphabet reduction. An important feature of alphabet reduction is it replaces a global constraint by a bunch of almost equivalent local constraints. A good example is the Hadamard code. Hadamard code encodes a d-dimension 0-1 vector by a 2-d dimension 0-1 vector. In the position corresponding to vector A, we put the dot product of A and X. Suppose we have a constraint Cx which returns 1 if and only if Ax is 0. To check whether an input vector x satisfies this constraint, we need to read every bit of this vector x. But if we are given a Hadamard code of x, we only need to read a constant number of bits. Now we have the technique of alphabet reduction. The first thing we want to do is to apply it to some parameterized problem. Observe that Hadamard code is about vector over finite field. A good starting point is to find some parameterized problem that are related to vectors. For example, k-vector sum problem is a good candidate. To make it simple, we consider a simple version of k-vector sum problem. In this problem, we are given k-vectors u1 to uk and a target vector t. The goal is to decide if the sum of u1 to uk is equal to t. Applying Hadamard code to this problem, we obtain a CSP problem. We expect the input of this CSP problem to be the Hadamard code of k-vectors. So first, we use the linearity testing to check if X is an Hadamard code. If it passes the C1 if it passes this testing, then there exists k-vectors v1 to vk such that X is very close to the Hadamard code of v1 to vk. Then in the C2 constraint, we check if each vi is equal to ui. Finally, we use the property of Hadamard code to check if the sum of u1 to uk is equal to t. Obviously, if the input instance of k-vector sum problem is a yes instance, then we can find an assignment such that all the constraints are satisfied. On the other hand, if the input instance is a no instance, then we show that one of the following must hold. Either there is a constant fraction of C1 constraints are not satisfied, or there exists an index I such that a constant fraction of C2 I-type constraints are not satisfied, or there are constant fraction of C3 constraints are not satisfied. Note that we do not have a constant gap in the CSP instance we create. If we apply the FGLSS reduction directly, we cannot prove the hardness of gap click. We observe that the problem comes from the C2 constraint, because we do not have a constant gap for this constraint. However, we do have a constant gap for the variables. We observe that every constraint in C2 is associated with a vector A. And for every vector A, if a constant fraction of A-type constraints fail, then there is a constant fraction of bad variables. Based on this observation, we modify the FGLSS reduction by adding a set of vertices that are corresponding to the assignments to variables. Recall that in the original FGLSS reduction, every vertex is corresponding to an assignment to constraints. So in our modified reduction, either we have a constant fraction of unsatisfied C1 constraint, or we have a constant fraction of bad variables. In each case, we cannot have a large click. So far, we have a reduction from a toy K vector sum problem to gap click. The next part of this talk is to show a reduction from the real K vector sum problem. In the real K vector sum problem, we are given K vector sets. The goal is to pick one vector from each set so that their sum is equal to a given target vector T. There are three problems we need to solve. The first one is K vector sum W1 hard? The answer is yes, when m is larger or equal than k square log n. The second problem is the reduction in FPT. Note that when m is large, we cannot create a vector in 2 to mk dimension in an FPT reduction. The third problem is how to test a vector is in a given vector set Vi. We solve this problem using a technique called multiplying random matrices. Recall that the original Hadamard code encodes a m-dimension vector by a 2 to m dimension vector. We know that 2 to m is too large. To reduce the vector size, we randomly pick L matrices and translate X into an LD dimension vector, Gx. This vector is partitioned into L block. Each block is a D-dimension vector. Then we apply the Hadamard code to each block, obtain an 2 to D dimension vectors. Note that 2 to D is small, and in each position corresponding to A, we put an L dimension vector. The result can be treated as a linear function from D dimension 0 vector to L dimension 0 vector. So, given any function from D dimension space to L dimension vector space, we first use the linearity testing to test if it is a linear function. Now suppose a function capital X passed the linearity testing. We know that there exists a vector V such that X is very close to FV. Our next task is to check that v is equal to g of x for some vector x in a given vector set v. How to do that? First, we prove a lemma. This lemma tells us that for every vector A, there is a unique vector x, such that v and gx have the same value on the position corresponding to A. However, this is not enough, because there might exist a vector A and A prime, such that v and gx have the same value on the position corresponding to A, and v and gy have the same value on the position corresponding to A prime. Our second lemma shows that this cannot happen. Finally, we show that our reduction will not translate a no instance to a yes instance. To summarize, we prove that k-click is W1 hard to approximate. The open problem is, can we find an FPD reduction which create a constant gap for the CSP problem? Okay, thank you.